Hey, Dr. Clark back at you here. In the last video we saw kind of the basic idea for how a simulation-based approach is going to work. Now let's take a look at an example problem where we put it into action. So the example we're going to do is called Comprehending Ambiguous Prose, and the setup is based on this paragraph. So what I'm going to encourage you to do is just pause the video here and read this paragraph. However long it takes, just pause the video and read the paragraph. Okay, hopefully we're back. Hopefully you've read the paragraph. And what this example came from is a famous experiment by Bransford and Johnson, 1972. Students were randomly assigned to one of three groups. Either they were given a picture before they read the paragraph, they were given a picture after they read the paragraph, or they weren't given any picture at all. And then they were asked to rate their comprehension on a scale of 1 to 7. And this is the picture. And what hopefully happens now is you realize after seeing the picture with the guitar and the balloons and the speaker and the young woman that some of the words start making more sense in the paragraph. So then you might wonder, oh, okay, oh, balloons. Well, if you've already seen the picture, then actually what's going to happen is those balloons are going to make more sense. So that's the idea. Does having a picture improve your comprehension of the paragraph or not? And this, has implications for children's books and literature and that kind of thing. How many pictures should we put into books and that kind of thing. So this was a test to see if there really is any value. All right. And there's three setups. Either they saw the picture before, after, or they were not given any picture at all. So the hypotheses would be these comprehension scores would either all be the same. That would be the null hypothesis, that the average comprehension score among sort of all possible people who read that paragraph, or at least one of them is different. We can also talk about it in terms of association. There's no association between whether or when a picture was shown and the comprehension of the passage, or there is an association. This is the data from the study. And what you can see is hopefully that people who saw the picture before looks like their comprehension is higher than those who didn't see the picture or those who saw the picture afterwards. And you can see that in the average comprehension scores, 4.95, 3.37, 3.21. But of course, this is just the sample data. What we really want to know is not just what happened in the sample, but what's true about all possible people who had done this study. So there's like a long run mean. This is just sample mean data. To compare them, we're going to do the mad statistic. So we take each X bar, subtract it from the other one. So we subtract these two, we subtract those two, and we subtract those two. Take the absolute value so they make positive numbers, and then average those three numbers together. And you find that the average of the absolute value of the differences is 1.16. The bigger that is, the bigger the difference we see in these three groups. Okay? But now we need to know, well, I don't know, what is 1.16? Is that big or not? So we're going to go to the applet now. And in the applet, what we need, well, first we need to go down Chapter 9, Comprehension. We're going to copy this data, okay? And then we're going to jump into the multiple means applet. Multiple means, because we've got multiple means in this problem. Clear it out, paste it in, use data, and now they make the dot plots for us here. 1, 2, 3 groups. We can click box plots and it'll draw those box plots for us. And you can see that the before group seems to have, on average, a little better comprehension. Down here is the summary statistics. Tells you the sample sizes, and it tells you the averages for each group and the standard deviations for each group. So this 4.95, 1.31 means that the average of these data are 4.95, and the standard deviation, that measure of spread, is 1.31. Okay, that's down there. And the MAD statistic gets computed automatically for you. If it's not checked as MAD, you can just check it to MAD, and it computes it for you. And then to run the simulation, we have to click that little shuffle button. And when we do a shuffle, what it's going to do is randomly assign these numbers, these comprehension numbers, to the three groups, after, before, and none. And then it will compute the means for each of those randomly generated groups and compute the MAD statistic of 0.25, and it'll plot 0.25 on the graph. And if we shuffle again, we'll get a different MAD statistic, and every time we shuffle, we get a different MAD statistic. And if we shuffle, say, 100 times, we get a whole bunch of them. And once you do it 1,000 times, you can see that there is a pattern to these MAD statistics. Kind of has that shoe shape to it. It's not bell curved. It's more of this up-down shoe kind of shape with a long tail to the right. Of course, it's stopped on 0 because the MADs are all positive. And so the question is the one we saw, the 1.158, is that typical from if we just randomly assign the data, or is it an extreme one? So let's type in 1.158, count it, and it looks like it's way off in the tail. In fact, out of 1,037 simulations, it never happened that it was as extreme or more as extreme as 1.158. So our p-value is 0. You can see we have very strong evidence that what we saw in the data is not going to happen by random chance. There must be something else going on. And I'll tell you what else is going on. They showed some people the picture before they read the paragraph, and that affected how their comprehension, right? I mean, it makes perfect sense. All right. So this is the kind of thing. You see the box plots, you get the summary statistics, you get the MAD, you get the simulation, and you get the p-value. And then you can make a conclusion. So because our p-value was less than 0.01, we have very strong evidence that at least one of the parameters is different. At least one of those mu's is different. We can follow up with pairwise confidence intervals to see which ones are different, and we're going to do that in section 9.2. But the dot plots would give you an idea. I'm guessing that the before is statistically significantly different than the none or the after. But I'm not sure we're going to be able to conclude that the none and the after are statistically significantly different. These seem to have a lot of overlap, and they're slightly different, but I don't think they're going to be statistically significantly different from each other. But I think seeing the picture beforehand will be statistically significantly different from not seeing a picture and from seeing the picture after you read the paragraph. So that's the kind of thing that we can do when we follow up with pairwise confidence intervals. But what we can conclude is at least one of these long run mu's, mu before, I think is different than the other two. It's what's going on. Okay, so hopefully that gives you a nice example of how to do a simulation-based problem with multiple means. Go through the simulation, get the p-value, see all the different data there, and you should be good to go.